So it's a pleasure for me to be here at this GCEP meeting. I just talked with Richard here in the break. I happen to be one of the early people involved with actually GCEP, and it's quite remarkable. As I remember, I think I was at the first GCEP Symposium, a very small meeting, even before Richard actually arrived at GCEP, and how it has grown and the impact it has had at Stanford over the years is quite remarkable. Really being the seed for all the energy projects here. So what I will talk about today is probably going to be much more fundamental than what you have heard before. And I've been involved in a couple of GCEP projects, very much together with, let's see, this pointed as together with Jens Norskov and Tom Jaramillo, really about CO2 reduction. This picture I got from Jens, which is, of course, he talked a lot about that yesterday, how to obtain sustainable fuels and so on. And I don't need to spend much time explaining what this is about. And also, when it comes to CO2 reduction, is of course very much to use CO2 and energy and transform that either through a gas phase catalysis process, as Jens indicated in the case of ammonia synthesis yesterday, or electrochemical process to generate fuels, but also actually chemicals. And I think in the long run, CO2 might be actually particularly important for chemicals. And I will mention that a little bit in terms of ethylene that we see are an interesting product in these systems. And for a rational catalyst design that we have had in our GCEP project, we have had this cycle here of synthesis, theory, very much, theory has been an important component to drive many of the ideas here, synthesis, test, and then characterization. And we have represented very much the characterization part of these GCEP projects. And I will talk about X-ray, how we have used X-rays up at SLAC, National Accelerator Laboratory. And I'm going to address two particular issues here. The first one is just CO2 reduction as a thermal process. As you can see, it undergoes a number of different steps in the reaction. This course is syngas reactions, or also with CO2 through the water-gas shift reaction, where you then bring in hydrogen, and this usually operates under very high pressure. The other is electrochemical. Instead of having the hydrogen coming in the gas phase, it comes via protons. And of course, you have an aqueous medium. Some steps might be similar to the gas phase. Some steps might be very, very different from the gas phase because you have proton and electron transfer involved with them. So I will talk about two approaches how we have used X-rays. The first one I picked because I think it can be interesting for this audience to see an example of how we are using the biggest facility here at Stanford, which is the linear accelerator up at SLAC. So I'm choosing one example which is ultra fast. This is actually the example that you see on the left is CO oxidation, which is not, of course, you're generating CO2 or not reducing. I will speak about the reducing of CO2, and I'm not going to speak so much about that topic, but it was unique that study opened up for us to actually see something which is the holy grail in chemistry, which is the transition state, or the transition state region, which controls all chemistry. And with this new tool that we have at SLAC, and many others are coming up around the world, including in Europe and Japan and in Korea, etc. now, but SLAC was leading the way here, and SLAC are building also a new machine, is really opening up to study chemistry, what I call in real time, looking at chemical reaction in real time. And I'm going to define what that means in a minute. And then we have in situ and operando spectroscopy done at SSRL, where we are looking at interfaces under, and I will choose that electrochemical reduction of CO2, and particularly where we can learn some insight of some new interesting catalyst that has been generated here. So the first example is addressing, if you can see, intermediate species. And in all of these CO2 reduction processes, often is assumed, and it's very strongly, of course, put forward by theoretical calculations, that there will be a hydrogenation step. You have in here somewhere a CO molecule that has been reduced from CO2, and there is a hydrogenation step where you're actually going to add a proton to this CO, which, if you talk with Jens, it's going to be the rate limiting step in almost all of these processes. Can we see this species? Nobody have ever seen that species. It's both in this reaction and in the electrochemical reaction. And we're going to take it first the thermal route here to see if we can actually observe that species. And we are going to make use here of the linear coherent light source, and I think we are down here somewhere on campus, very low down. And the linear coherent light source make use of the linear accelerator. I see Greg Lowe sitting here in the front that was part of building that accelerator more than 50 years ago, and has been used a lot for particle physics experiment, but almost a little bit more than 10 years ago it was turned into an X-ray laser. And it's a fantastic machine. It can generate very short X-ray pulses down to actually 5 femtoseconds. I think actually it's been even down below 5 femtoseconds now. You can tune it. And it can generate very, very intense pulses, 10 to the 12 photons per pulse, etc. I'm not going to speak too much about that. So these projects typically involve big teams for people to do this complex experiment during a very short time when you have access to this accelerator. So you have to imagine now, you have a few days and you are the only one using this accelerator for your experiment. So you better have it working, so to speak. So you need these big teams, and there is a lot of people involved here, and also one on the theory side is Jens Norskov, but also many other people like Frank Abel Pedersen in SunCat, and then a lot, I should also mention Hirohito Ogasawara at SLAC, SSRL, very important key person in this experiment. So let's ask about the fundamental understanding here. This is a very simple energy diagram of reaction. We are going from the left, potential energy, A plus B, going to AB. And if we have no catalyst, there's a very high barrier. With the catalyst, we open up a new pathway by having species on the surface. And as you can see here. One of the big questions is, can we see these reaction intermediates? Can we actually detect them as they are small sink on the reaction, so to speak? And often people are trying to do this with operando spectroscopies, let's say at SSRL, but the important intermediate actually might be very short-lived. They might only live for a very short time. And under steady state conditions, the population of them is almost zero. It's a very small population. So we need to develop techniques so we can populate them very quickly to see them. The other thing is, can we probe transition states? And that was actually our CO2 study that was published in Science 2015. I will not going to talk about that so much today, but actually that is, of course, also very important. Both of this intermediate and transition state, can we see these? We want to do time resolve measurement to see that. And typically people do that all the time when they do chemistry. We measure reaction rates. I put this up a little bit like this, that when you do a kinetic measurement and measure reaction rate, you actually are often measuring how often a reaction event is attempted and if it is successful or not. You're never really measuring as the reaction is happening. You're only measuring how often you have an attempt to make a reaction and if it is successful or not. And that might be just a few, what called turnover frequency, a few turnovers per second or even per minute in many cases per active site. So you can't see really what's happening as the reaction is occurring. So in order to do that, you really need to start all the reaction events to happen at the same time. You need to pump the system to really stimulate it, and then you can follow it. And that's what we call, instead of a kinetic, we call it dynamics. We do the dynamic studies. And so what we are thinking here is that we simply have molecules on the surface, we pump it with an optical laser, we put in a lot of energy there. Actually, it's more a pumping of the electronic system in the substrate that couples to the molecules on the surface, and then all of them get kinetic energies at the same time, and they can start to react, so to speak. So we want to now look at that particular CO2 reduction, and the interesting step here is CO reduction. Can we see these HCO or COH species being formed when we have a CO molecule being reduced with hydrogen? And the first question, can we see it? With the hydrogen attached to the carbon atom, will it attach to the oxygen atom, or is it a stable intermediate, or what will we see? And first of all, we did experiment, actually this is done in Stockholm, where you put an optical laser and you look with the mass spectrometer. We can see that mass 29 that corresponds to this CHO or COH is coming off the surface when we put the laser on. We can even see a further reduced form, which is all formaldehyde. So something is happening there. Then we go and do these things now at LCLS. And what you see on the left here is spectra, what is called X-ray absorption spectroscopy. It means that we are taking an electron in the core of oxygen 1s and lift it up into the unoccupied states. So what you see there as the strong resonance on the left side, which is actually the black spectrum, is actually CO on the, in this case, Ruthenian surface before you put in an optical pump. And the resonance you see there is called the 2 pi star level, which is the antibonding orbital between the carbon and the oxygen of the pi system, the antibonding orbital, because it's unoccupied. As you are now looking at it after a few picoseconds, after you pump the system, you see that there is a tail, which is the red spectrum there, coming in, and it's marked there with a grayish, where that intensity comes up. And we then go ask ourselves, what is this intensity coming from? And that's what you see in the lower part there of the figure, is simply theoretical calculation of spectra that we have taken along the reaction pathway that was calculated. I will come to that in a minute. So you can see the CO species is well reproduced. If you add the hydrogen on the oxygen side, we should see a shift of intensity to higher energy, which is the green there in the calculated spectrum, and we clearly don't see that. If we instead attach the hydrogen to the carbon side, and we can have different type of species there, we can have the more stable HCO, which is the red one, and then we can have something which is called close to the transition state or on its way to transition state, and you can see a number of spectra. Well, clearly, we are seeing a distribution of these coming up, and this directly tells us we are seeing the HCO species, and the hydrogen is attached to carbon, and there are a number of distributions. Then we can look how the time evolution of this is by looking at the intensity as we delay between the optical laser and the X-ray laser. We are delaying the time as we are looking at the species after we pumped it. And as you can see that this actually peaks at around 1.5 picosecond. So obviously the CO or the hydrogen is running into each other and forming these HCO species, but it's not stable. Actually, it will decay. So it tells us that this intermediate is only metastable. And we are also seeing species on the way to the transition state. So then we went into the theory, and this particular calculation was done by Frank Abel Pedersen. What you see is a free energy diagram, so to speak, as a function along the reaction coordinate. You have different temperatures here. And let's just look at it at very low temperature. You see C plus H, and then you see the going over the transition state, and then you see the final CHO being formed. And you see the CHO is actually at higher energy than the C plus H, which means that it's not stable, it's metastable. If we can go further also to formaldehyde, which is even going up higher in energy. If we add temperature, we get free energy, which of course corresponds adding into entropy into the system. And as you get it very hot, you can actually indeed see that you can desorb these different species because the free energy of the gas phase, even though it's a radical state, becomes lower. That's why we could see it in the gas phase. So this demonstrates that actually indeed we can observe this CHO species. That is the first time this is seen in an experiment, and that it actually is indeed metastable. And we can actually derive like a mechanistic picture here with different time scales. We can think about also chemistry a little bit in different time scales, because you have on the left there it's CO plus H. As time goes on an axis here towards the right, you have then on the upper part there the CHO being formed. But on the lower part, you also have a competing mechanism, which is hydrogen being desorbed from the surface. And these are competing with each other. And eventually, on much longer time scales that we have measured in a different experiment, I didn't speak about that, we can actually see CO leaving the surface, actually being trapped in another metastable state called the precursor state, sitting just outside the surface. So we can actually follow all this now in real time. And I think this is giving insight into these processes that are very important. So we can observe transient intermediate state, and I'm indicating them actually being at higher energy than the initial state, because this is simply metastable states. So let's go now to the second part, which is electrochemical here, reduction. How much time do I have left? So I should take this very quickly. What we have recently done is that we have actually discovered a very interesting copper nanocube catalyst. If you actually run CO2 reduction in electrochemical environment, and this was discovered by an accident. One of the postdocs had a leaking electrode, so they actually got chloride into the solution. They actually observed this cubes structure of copper as you reduced it, so to speak. And it turns out that in this experiment using an online mass spectroscopy measurement, it had a very high selectivity for forming ethylene compared to methane, although we don't know the total activity, which is something we are measuring right now in collaboration here at Stanford with Tom Jaramillo and Chris Hahn's group, but we are detecting all products. But we are seeing this very interesting change in selectivity. And we can actually also look at all the different single crystals, and we can see that these cubes are very unique, that when we compare how much ethylene is formed compared to methane, it's a change of a factor that varies depending how you do the measurement between 10 or 100. We think in the relative change of ethylene to methane. And none of that is even observed on different single crystal surfaces. And of course, for forming ethylene, CC coupling is very important. This is an area, intense theoretical work in Jens Norskov's group to understand all this detail. We can see a similar effect also if we do CO reduction, which is something that very much Matt Cannon did many recently on these type of systems. And we see the similar phenomena also done at different pH, where the copper cube seems to be responding also with the pH change, just like a single crystal, but we see this change in selectivity. And this, of course, opened up the question originally, what is this caused by? Are we forming some sort of copper chloride precursor here in this that is actually being reduced? That's maybe why it looks very cubic. And we went to SSRL and did in situ X-ray absorption spectroscopy measurement of the copper K edge. I don't have too much time to go through all this in detail, but what we actually found was that no, there is no copper chloride being formed. Instead, it looks like there is a copper 1 oxide being formed when you are when you are under oxidation conditions, and then you actually reduce that, and the only thing you see is a metallic copper. And you could actually generate, without going through the details, very similar oxidation without the chlorine present, and then you generate, instead of copper 1 oxide, you generate copper 2 oxide at much higher potential. But as you reduce both of them, you get actually the same type of selectivity change with a lot of ethylene compared to methane being formed. And we now also learn that alcohols are being formed here as well, in consistency with also what Matt Cannon has seen. So one question is, what is making this change in selectivity? And we are discussing this with many people, and I just put up 3 different hypotheses, I call it. I think it's good in science, think about hypotheses. One is that I will say a little bit more about subsurface oxygen is one hypothesis. There can also be diffusion limitation, because these are very porous material, and this diffusion limitation could make that the proton transfer is not getting in everywhere, and you can change the pH. That could also change the chemistry. That's one hypothesis. And then finally, grain boundaries. And what we've done is an in situ XPS measurement under reaction conditions, and I just finalized by saying that as we are running the reaction in the electrochemical and taking out the sample but still being wet, we're actually seeing that there are oxygen left in the systems. And this is now an interesting aspect to understand, and why that is happening, and if this actually is very important for the chemistry. But it's only one of these hypotheses. So let me finish with this statement, and I take some questions. Thank you very much for your attention.
We have questions. Maybe, yeah, thank you. We're getting the microphone.
In these potential curves that you show in the first and second slide, what's the significance of the 3 humps? Is that a property of the catalyst only, or is that something else?
You mean in the last part here, or in the
very first, in the fast process? You have 3 humps, and is that good or bad? I mean, the first hump is lower, the second one is higher, and the third one is lower again. Is that something you can control?
I'm not sure I exactly know which humps you are talking about.
Not this one, at the very beginning.
That was just a schematic of the reaction.
Yeah, right.
So you mean
you
here?
Have 1, 2, 3 humps.
Yeah, so this is just a schematic, so to speak. And of course, as we are running this with an ultra-fast technique, you could in principle see population as a function of time as you are populating these different humps. Yeah. So this is of course the fascination with the new experiments we can do in X-ray laser, where you can follow this in real time. You can actually follow them the time evolution, how you're populating these humps, because you get A plus B started to react at the same time with all over the surface. And then there will be a time evolution. Let's say they go to the first little well there. They will trap there for a little while, and then they climb over to the transition state, and they go to the second well. That will come a little bit later, etc. So this opens up the potentially to follow all of these details with these new type of techniques.
Anders, you start this off with a laser pulse, right?
Yes.
To initiate things. But by the same token, laser pulses, you've shown desorb things. So I guess I'm curious about how to think about zapping this with a laser pulse, and you're following chemistry. What does it have to do with chemistry driven by thermal processes?
Yeah, this is a very good question. So we have looked at this also from a theoretical point of view. So what you do with the laser is that during a very short time scale, you actually change the electronic structure, in particular in the metals, you generate a hot electron distribution. This will actually couple to the molecules to set them moving, so to speak. By the time the chemistry has taken place, this type of excitation has decayed down, and the molecules are still moving on let's say, the potential energy surface that we expect under a thermal process. So the process how they get kicked are of course different, but as they are moving and starting to colliding, they're going to move on the potential energy surface, similar to a thermal process. And of course, since it's in a very high temperature state, that's why you can get everybody moving at the same time. You will have also the potential energy surface, of course, will be moving slightly different because of phonons and so on in the substrate. And some of the theory we have here also, we have included higher temperature in terms of the entropy contribution in these processes. And we see it doesn't really modify things very dramatically. The same underlying chemistry is there, so to speak. Yeah.
Maybe I can ask one more question. So you showed us that your intermediate is this HCO. It seems to be a very important discovery.
Yes.
But yet it's high energy and therefore short-lived. Can you think of ways now to study how to control the fate of that intermediate?
You mean how we can, you mean control the intermediate or?
Both control and monitor.
Yeah, I mean, we have now the way to monitor it. We are developing these techniques also, so we will hopefully very soon measure this with a factor of 1,000 more efficiency, so we can control, we can measure many different things, how we put in different kinetic energies and so on. There's another area where we are very interested in, where we also use the SLAC, is actually to see if we can control chemistry with radiation. And as we probably heard, like Jens talked about yesterday, that we have to go on this sort of linear scale. He talked in the terms of the ammonia synthesis, where you have to dissociate the molecule, and the molecule is then also, the fragment is bound to the surface, and these are opposite little bit relationship to the bond strength. So if the bond strength to the surface is very strong for the final product, the barrier is low, but then it's very difficult to get the species to react further, for instance. So we are investigating terahertz radiation, if we actually, by using that, can change the selectivity and actually modify only one of these species, not the other one. And we actually have the first indication that indeed you can do that. And we think this is an interesting avenue for future, probably not going to be that Exxon can use it tomorrow, but it could be still an avenue to actually think about controlling chemistry in a different way. So that is also what we are looking into.
Great. Thank you very much. Let's thank Anders again.